Hey everybody, it's Beej with Lambda School. Today we're going to be talking about CPU interrupts and how these things work. So the objective here is to understand and describe interrupts and see how they're useful. So we'll be talking about what an interrupt is, how an interrupt is raised, and how interrupts are handled. So, what are interrupts? Interrupts are commonly generated by peripherals. So what does this mean? So we might have a peripheral attached to the computer, like a keyboard or a mouse or something like that, and the peripheral might be demanding attention for some reason. Say a keyboard, demanding attention because the user has finally pressed a key. Remember, CPU is really fast, so a CPU can get tons and tons of work done between individual key presses that a glacial human is producing. And so interrupts are a great way to have the CPU get notified that, hey, something needs to be handled besides the regular work that you're working on. So if the CPU is in the middle of something very complicated, what it can do is it can save the entire state of the processor onto the stack. And it needs to do this because it needs to save its work so that it can come back to it later. So if it's in the middle of computing pi or something like that, it saves the processor state on the stack. This means we are saving the registers, we're saving the flags, we're saving the program counter, things like that. Everything that we need to do to restore the state of the processor later so that it can continue exactly where it left off. So what happens after the interrupt occurs is that the program counter moves from what it was doing to a different address in memory where the interrupt handler program is. This is another piece of software that is designed to do something in particular when a certain event occurs. So maybe if a key event occurs, then the interrupt handler is supposed to deliver that key through the operating system or something like that. But eventually the interrupt handler is done with its work, and when that happens, we restore the CPU state by popping everything off the stack, including the program counter, and then the CPU picks up where it left off as if nothing has ever happened. So what are some of the details of this? When the interrupt occurs, we need to set the PC to point to the interrupt handler. So the PC needs to move to wherever the interrupt handler is in RAM so that that code begins executing. So in order to make this happen, because there are typically different kinds of interrupts on a system, like let's say for the sake of example, our system has 8 different interrupts that can be raised, then we need to look up where the handler is for each of those one individual interrupts. And so a lot of CPUs do this by using something called an interrupt vector table. This is just a table that's stored in RAM somewhere, like an array of pointers to functions. You can think of it like that. This has an array of pointers to interrupt handlers. And so what might happen is if, say, interrupt number 2 occurs, we look at the second element in the interrupt vector table, and that tells us where to move the PC to handle that interrupt. So we have, again, an array of pointers to handlers, 1 pointer per interrupt. So this table has to be stored somewhere in RAM. Some CPUs store it in low areas of RAM. Other CPUs store it in high areas of RAM. Depends on the architecture. But let's do an example with our simple 8-bit computer. So we have a program here on the left column. We'll talk about that more in a minute. In the center column, we have the interrupt vector table, which again is stored in RAM. And then on the right column, we have the output from this program. So we'll trace through this program as it runs, and then we'll simulate an interrupt occurring in the middle of the program run. So how do we read this? The code column on the left. The numbers on the left in hexadecimal are the address that these instructions begin at. So the PC is currently pointing at instruction LDI R0,0, which is at address 0. At address 3, we have the next instruction. At address 6, we have the PRN instruction, and so on. And then in the center column, the interrupt vector table, again, the left column of that, F8, F9, FA, and so on, that is the address. So this is further along in memory, higher up in memory. And then the number right of that is the pointer to the interrupt handler for that particular interrupt. So let's look at that first line, F8, address F8. That is the interrupt handler for interrupt 0, whatever that is. Maybe that's a timer interrupt. Maybe it's connected to some piece of communications equipment, something like that. Right now it's pointed to 0, seemingly uninitialized. F9, I have a comment there that this is the keyboard interrupt. So we have a different value in there. We have 0C stored at address F9. This is a pointer to the interrupt handler for the keyboard interrupt. Remember, a pointer is just an address. So 0C is the address of the keyboard handler program for the keyboard interrupt. And if we look at the left column again under code, we can look down to address 0C, which is where the keyboard interrupt handler starts. It's also highlighted there. And we see that there's some code there. This is what the interrupt handler does. Let's read this code and see what happens. Starting at address 0C, we load register 0 with the value 65. Now you might not recognize that right off the top of your head, but 65 is ASCII for a capital A. And then at address 0F, we print that value out as an alphanumeric character. So we print R0, so that should print a capital A. And then line 11, at address 11, hex, we have an iReturn instruction. This is return from interrupt. So when this happens, this is going to do all the stuff about restoring the state of the code to what it was before. It's going to pop the PC off the stack. It's going to pop all the registers off the stack, all the flags off the stack, and then the interrupt will be completed. We'll say it has been serviced, and then the code will continue where it left off. So that's the interrupt handler here, but what about the actual code? Starting at address 0 up through address 0A, what does this code do? Well, looking quickly through it, it looks like we load register 0 with 0, register 1 with 6, we print register 0 on the screen, so that'll print as 0, then we increment register 0, so it becomes 1, then we jump to whatever register 1 is, which is 6. So we jump back to address 6. So we got a little loop in here between address 6 and address A. That loop prints register 0, it increments register 0, and then it jumps to itself. So this is a loop that's going to print out numbers. It's going to print out 0, 1, 2, 3, 4, 5, and so on. So let's trace through this and watch this happen. And then we'll have an interrupt occur in the middle of it and see how that affects our output. We'll have a keyboard interrupt occur. So first thing we do is load R0 with 0, then we load R1 with 6, then we're going to print R0. The value is 0, so we see in our output column as 0 appears. Then we're going to increment R0 so it becomes 1, and we're going to jump back to address 6. And then we're going to print R0 again. And we're going to increment R0. And we're going to jump back to R1. And we're going to print R0 and increment R0 and jump back to R1. And then we're going to print R0. This is what our program's doing. It's printing out numbers from 0 to infinity. Then let's say right now, right before this increment instruction occurs, let's say the user hits a key. The keyboard interrupt is raised at this point. The CPU is going to stop what it's doing. It's going to say, hey, instead of running this increment instruction, here's what we're going to do. We're going to push all the registers on the stack, including the program counter. We're going to push all the flags on the stack. We're going to push everything on the stack that we need to in order to restore our work later. Because we got to get back to this very important task of printing out the numbers between 0 and infinity. But first, I want to handle this interrupt. So we save all that stuff on the stack. We go to the interrupt vector table for interrupt number 1, which is the keyboard interrupt. And we say, where is the handler? Where do I need to put the PC right now to handle this keyboard interrupt? And we see at address F9, the keyboard interrupt handler is located at address 0C. So after we push all that stuff on the stack, we got all our work saved, we can come back to it later, no problem. The PC jumps to address 0C to handle the interrupt. Now this is code we've already talked about earlier. This is where we load R0 with a capital A in ASCII, and then we print that out. And so we see A appear on our output. And then we've got our iReturn instruction. This will pop all the work off the stack that we had saved earlier when the interrupt occurred, including the program counter. The program counter was at 8, so it's going to restore the program counter to 8. R0 has been restored to the value of 3, what it was before. R1 has been restored to the value of 6. Everything is just as we left it before. So indeed, if we increment R0 at this point, it becomes 4, and then we jump back to R1, and we print it out. And then we increment R0 to 5, and we jump back to R1, and we print it out, and so on. So what's happened here? We can see in the output that the program typically just prints incrementing numbers, 0, 1, 2, 3, 4, 5. It's totally happy doing that. But when a key is pressed and the keyboard interrupt is raised, it stops doing what it was doing. It jumps to the interrupt handler, which it knows the address of from the interrupt vector table. It handles the interrupt in there by doing whatever it is asked to do. And in this contrived example, we just had it print out a letter A. Most frustrating keyboard ever. Only prints out A no matter which key you press. We'll send that back to sales and marketing and see if we can do something with it. But after the A is pressed and the key interrupt is handled, we go back to our regularly scheduled processing. And we see our 4 appear and our 5 appear and so on. The A from the keyboard interrupt has effectively interrupted the work we were doing and did something else instead. And that is, in a nutshell, how interrupts work. So here on this slide, you can go ahead and pause it. I've got some questions here that are meant to challenge your thinking and knowledge surrounding interrupts. So go ahead and pause the video here and tear into these. And thanks for watching as always.